Fluid dynamics is the study of fluids that are in motion, relative to a frame of reference. The fluid motion is usually characterized by a fluid velocity that can vary in magnitude and direction, in space and in time. Examples of situations that involve fluid dynamics include the flow of water within a pipe, the flow of spray out of a nozzle, and the flow of air around the wing and body of an aircraft. In this last case, even though the air is generally stationary, it can be considered to be moving with respect to the airplane. A flow can be classified into steady and unsteady. Suppose we measure the fluid velocity at any macro point in a flow field. By macro point, we mean any small volume, which is several orders of magnitude bigger than the molecular scale. If we find that the fluid velocity at any macro point in the flow field doesn't change with time, then the flow is a steady flow. On the other hand, if the fluid velocity at any macro point in the flow field does change with time, then the flow is an unsteady flow. Steady flow can be further divided into laminar and turbulent. Unsteady flow can be divided into laminar, turbulent, and droplet flow. In this course we will study steady laminar and steady turbulent flows. Now let's examine the types of steady flow. In a laminar flow, fluid flows in smooth parallel streamlines, with no flow across the streamlines. One example of a steady laminar flow is that of water flowing slowly from a faucet. The water flow is smooth and continuous along smooth and parallel streamlines. Also notice that you can easily see through the water, since the flow is smooth and clear. Another example of a steady laminar flow is water flowing slowly in a pipe. If we inject a dye in the flow, through a small nozzle, as shown here, the dye traces the motion of a streamline. Notice that the streamline position is constant, since the flow is steady. And notice also that there is no flow perpendicular to the streamline, or in other words there is no cross flow. And therefore the streamline is smooth and continuous. In turbulent flow, the flow is not smooth. There's mixing and cross flow across streamlines. An example of steady turbulent flow is water flowing full blast from a faucet. Observe that the flow is not clear and smooth, due to the mixing and cross flow of the streamlines. The flow is said to be chaotic, and not predictable. The faucet flow shown here is still considered a steady flow. This is because if we measure the average fluid velocity inside an arbitrary large enough volume, which is about a 2 mm³ volume in the shown flow, we will find that the average fluid velocity inside that volume is nearly constant. What is the difference between steady laminar and steady turbulent flows? Recall that the definition of steady flow is that the average velocity inside a small volume is constant. For laminar steady flow, the small volume is on the order of microns. Any smaller than that, and you'll observe fluctuations due to molecular motion. For turbulent steady flow, the small volume is on the order of millimeters, or larger depending on the scale of the flow. Any smaller than that, and you'll observe fluctuations due to turbulence, and therefore the fluid velocity will not be constant. The smaller the volume, the more violent the fluctuations will be. Now let's examine the three types of unsteady flow. One example of unsteady laminar flow is vortex shedding over a blunt object, such as the circular cylinder shown here. Vortex shedding over blunt objects is a fluid flow phenomena that causes a symmetric flow configuration to result in an oscillating asymmetric flow. For example, in the flow over a cylinder, the inlet flow has a uniform velocity in the horizontal direction. As the inlet fluid velocity increases, two symmetric vortices behind the cylinder start to form. Then, as the inlet fluid velocity increases further, the flow behind the cylinder starts to oscillate. By alternately growing one of the vortices behind the cylinder and collapsing the other. At this point, the flow is unsteady. But, it is still considered a laminar flow. This is because the flow is not chaotic, it is periodic and predictable. Also, if we take a snapshot of the flow, we will observe that the streamlines are smooth and parallel, with negligible mixing and flow across the streamlines. As the inlet flow velocity is increased further, the flow starts to develop secondary vortices behind the cylinder. Further increasing the inlet velocity, increases the complexity of the wake, and causes the wake to eventually become chaotic and turbulent. One example of unsteady turbulent flow is water flowing at an intermediate rate from a faucet. Note that the flow shifts in time from one flow regime to another, and therefore, is unsteady. Also, note that the flow is not smooth, and therefore, it is considered a turbulent flow. A second example of unsteady turbulent flow is water flowing over blunt objects, such as water flowing over rocks in a creek. Note that the flow changes with time, due to vortex shedding behind rocks and obstacles in the creek. Therefore, the flow is unsteady. Also, note that the flow is not smooth, and therefore, is turbulent. Droplet flow is an unsteady flow, where the flow rate is low enough, such that surface tension effects become significant. One example of droplet flow is water dripping from a faucet. Another example is aerosol flow. A streamline is an imaginary line that is drawn within a steady flow field, such that every point on the line is tangent to the flow's velocity vector. In other words, no flow passes perpendicularly across a streamline. Shown here is a streamline in the flow field of an airplane model in a wind tunnel. Practically speaking, we can think of a streamline as the trajectory that a particle of zero mass will follow when released into the flow from a fixed point in space. Depending on the location of the point from which the massless particle is released, we will get a different streamline. One technique to visualize how a flow looks like is to release particles from a rectangular array of points. Particles released from each point trace one streamline. Therefore, the particles released from the array of points trace an array of streamlines, which help us visualize the entire flow field. Notice that in the flow field around the airplane model shown here, the streamlines curve around the airplane's body, since no flow can pass through the airplane's skin. Also, note that no two streamlines intersect, since if that occurs, then, it means that there is flow that is not tangent to the streamline. In other words, there is flow that is perpendicular to the streamline. This violates our definition of a streamline. In fact, these are the two main characteristics of streamlines, namely that, they do not intersect with solid boundaries, and they do not intersect with each other. In studying fluid mechanics, we can use either one of two distinct reference frames: the Lagrangian reference frame, or the Eulerian reference frame. When studying fluid flow using the Lagrangian reference frame, we focus on an individual particle, and study the fluid conditions it encounters as it moves within the fluid, over a certain period of time. When studying fluid flow using the Eulerian reference frame, we focus on a specific location in space, and study the properties of the fluid that is flowing through that location, and how they change over time. The Eulerian reference frame is usually easier to work with when studying simple, steady-state fluid problems. The Eulerian reference frame also mimics the readings of the usual instruments that we often use to measure fluid properties, such as a pressure transducer that measures pressure at a fixed point in the flow. For these reasons, we will limit our following study of fluid dynamics to the Eulerian reference frame. The velocity of a fluid describes how fast a fluid is moving at a certain point in the flow. Velocity is denoted by a lowercase v, with an arrow on top to indicate that it's a vector quantity. But if we wish to know how much fluid is crossing a given area per unit time, we need to look at the total flow rate over that entire area. The rate at which a fluid is crossing a certain area can be described in two ways: by its volumetric flow rate, or by its mass flow rate. The volumetric flow rate of a fluid, through a certain area in the flow, is the rate at which a given volume of fluid crosses that area, per unit time. It is described by the symbol, capital V, with a dot on top, to indicate a time derivative. In its general form, the volumetric flow rate is equal to the integration of the velocity vector, dotted with the infinitesimal area vector dA. Recall that the dot product means that any component of the velocity vector that is perpendicular to the area vector dA is cancelled out. In other words, if the velocity vector v is tangent to the area dA, then the dot product of v dA is equal to 0. To simplify the equation, we first assume that the velocity vector v is always parallel to the area vector dA. This allows us to change the dot product of the two vectors v and dA to a simple multiplication of the scalar magnitude of v times dA. We can simplify the equation further by assuming that the velocity is uniform or constant over the entire area A. This assumption allows us to solve the integration in the equation for the volumetric flow rate as the simple multiplication of the uniform velocity v times the total area A. The units of volumetric flow rate is meters per second for the velocity units, times meters squared for the area, or meters cubed per second. So the value of the volumetric flow rate flowing through a certain area, such as a pipe's cross-section for example, is equal to the number of meters cubed of liquid that cross that area in 1 second. The mass flow rate of a fluid through a certain area in the flow is the rate at which a given mass of fluid crosses that area, per unit time. It is described by the symbol, small m, with a dot on top, to indicate a time derivative. In its general form, the mass flow rate is equal to the integration of the density times the velocity vector, dotted with the infinitesimal area vector dA. Assuming the density is constant over the entire area A, which is a reasonable assumption for an incompressible liquid, we can take the density term out of the integration. Assuming that the vectors v and dA are always parallel, we can replace the dot product of the two vectors v and dA by a simple multiplication. Finally, assuming the velocity to be uniform over the entire area A, we can solve the integration as the multiplication of v times A. Hence, using the aforementioned assumptions, we can calculate the mass flow rate as being equal to the density, ρ, times the uniform velocity v, times the total area A. The units of mass flow rate is kilograms per meter cubed for the density units, times meters per second for the velocity units, times meters squared for the area. And so we have kilograms per second for the units of mass flow. So the value of the mass flow rate, flowing through a certain area, such as a pipe's cross-section for example, is equal to the number of kilograms of liquid that cross that area in 1 second.